Okay, we're finishing up with notes from 10.3b. Last example here, example 2. An object moving along a curve in the xy plane has position x of t, y of t, and dx dt, which is 2 sine of t squared. The derivative is not explicitly given. At times t equals 2, the object is at position 3, 5. Find the x-coordinate of the position of the object at times t equals 4. So we're trying to find the final position of this object, which is x of 4. Well, to get to x of 4, we need to have an initial position. So we're starting at what they give us, which is x value of 3. So remember, to find the final position, we have to provide the initial position plus the displacement, this change in position that will take us from the initial position to our final position. So we're going to set up an equation. X of 4 is what we're after. X of 2 is our starting point. To get from x of 2 to x of 4, we're going to find the net change in position. So the definite integral of from 2 to 4 of x prime of t dt. So we can use our calculator, find the definite integral from 2 to 4 of 2 sine of 2t squared, and that'll produce us with negative 0.11528. So we're starting at position 3. We go backwards, or the negative direction, negative 0.11528, and our final position will be 2.885. Okay, so the third value can either round or truncate. Either one is fine. So part B, the value of dy over dt is negative 6. Write an equation for the tangent line to the curve at this point. So, or at the point x of 2, y of 2. Let's see. Well, x of 2, y of 2, we know the ordered pair that's given to us at the beginning of the problem, 3, 5. Okay, so now the only thing missing is our slope, since we're asked to find the equation of the tangent line. So let's see. Slope is dy over dx, all right? And using parametric formula to expand that further, we know that dy over dx can be expanded into dy over dt over dx over dt. Well, we have dy over dt, which is negative 6, and we have dx dt, which is 2 sine of t squared. So then the only thing we need to do is to evaluate the dx dt at 2. So plug 2 in for t. So we get 2 sine of 2 squared. So dy over dt over dx over dt evaluated at 2. We get negative 6 over 2 sine of 4. So there we have our slope. We have our point. And we plug into our equation, tangent line equation. Part C, find the magnitude of the velocity vector. So magnitude, another word for that is find the speed. So to find the speed, we just take the square root of x prime of t squared and then y prime of t squared. Evaluate both of them at 2, and we simply can leave it in this form, or we can combine it, simplify it to be a decimal value. For D, for t is greater than or equal to 3, the line tangent to the curve has a slope of 2t minus 1. Find the acceleration vector at time t is equal to 4. Well, let's see, what are we looking for? We're trying to find the acceleration vector, which is essentially x double prime of 4 and y double prime of 4 with these two x and y components. Okay, let's think about slope. Slope is dy over dx. Well, we know dy over dx. That's provided for us as 2t minus 1. And if we can expand this further, right, dy, we can think of dy as dy over dt. We can think of dx as dx over dt. So our slope is 2t minus 1. Well, let's see. We have dx dt. Right, that is given to us at the beginning of the problem, which is 2 sine of t squared. So we can replace dx dt with 2 sine of t squared. So we have dx dt. We have an expression for slope. So now the only thing missing is dy dt. So if I want to solve for dy dt, I can do cross product, or multiply the 2 sine of t squared to the other side. So now we have an expression for dy dt. So I can now evaluate the derivative of this expression at t equals 4, and that will produce me negative 108.408. So I use the n-deriv feature in the calculator, and if I want to evaluate the dx dt 2x over dt2 at t equals 4, then I can just plug in, find the derivative of 2 sine of t squared, and then plug in 4. So this should be d2x over dt squared and d2y over dt squared. So I'm finding the second derivative of x of t and y of t. And now I have the acceleration vector at time t equals 4.